So our next lecture is on continuous linear transformations. So we already read that nonlinear space and Banach space. So that is a transformation on a nonlinear space as well as Banach space. Now suppose n and n dash, these are the normed linear space over same field. So remember this, it is over same field, either it is real or complex, and let T be some n to n dash be a linear transformation. So what is the definition of linear transformation? It satisfies two property. Property number 1, T of x plus y, which is equal to Tx plus Ty, and property number 2, which is T of alpha x, so that is alpha time T of x. So if any operator, any mapping satisfy these two property, that is called a linear transformation. So what is the definition of linear transformation? This is one nonlinear space and this is second nonlinear space, and T is some mapping from n to n dash, right? Or this and this are nonlinear space over same field, which is either R or C, right? So this is a same field, either R or C, if it satisfies two property. Property number 1, T of x plus y, which is equal to T of x plus T of y, and property number 2, which is T of alpha x, which is equal to alpha time T of x. So this x and y, these are a member of norm space N, right? And alpha is any scalar which belongs to the field. If field is real, then it is belongs to R. If field is complex, then it is belongs to C. Clear? Now this is a definition of linear transformation, so which is very important definition on on a nonlinear space. After this definition, we have a very important result, that is on a bounded linear transformation. So first we understand the definition of a bounded linear operator. So here we understand the definition of linear transformation. So any linear transformation is said to be bounded. So next is definition of bounded linear transformation. A linear transformation T, which is from n to n dash, where n to n dash is a nonlinear space over same field. So this is said to be bounded. It is not a bounded set, it is a bounded operator. So remember, this is a bounded operator, a bounded linear transformation, bounded mapping. Now if there exists some positive number k, positive real number k, such that it satisfies this property, norm of Tx less than equal to k time norm of x for every x belongs to n, right? So this is a definition of a bounded operator, bounded linear transformation. Now it means if this is a n nonlinear space and this is again n dash nonlinear space, and T is mapping from n to n dash. So it is a linear transformation from n to n dash. So n has its own norm and n dash has its own norm. Clear? So if x is element of n, then it has norm x. So its image is tx, so that has a norm this dash. So these norm and these norm, they maybe have different norm and they maybe have same norm. So in the definition we are using the same, but it may be different. If it is represented in term of dash, then it will be a tx dash. If it is represented in term of simple norm, so this is a norm of x. So we generally write as a same norm of tx less than equal to k into norm of x. But you must understand that this is a norm of n. It may be any norm, and this is a norm of n dash, right? So these may be same, these may be different. These are norm related to n dash. This is a norm related to n. If these norm are same, then they will be same. Otherwise, both the norm linear space have a different norm and it may be have a same norm. So remember this as per point. So this is a definition of norm linear space. So after norm linear space, this is very important result normally expected for examination. If n and n dash is a norm linear space, right, over a same field, then the following statement are equal. Number 1, T is continuous. So what is the definition of continuous? If xn approaches to any sequence in n approaches to x, then its image is approaches to its image. Second, T is continuous at origin. So x is replaced by 0. If xn approaches to 0, then txn approaches to 0. So this is a 0 of n dash. Remember, this is a 0 of n dash, this is a 0 of n. Third is T is bounded, that we already know the definition. Fourth is, if S is a closed unit sphere of n, then its image T of S is a bounded set in n dash. So these are the four properties, and my aim is to prove that the following statements are equivalent. It means first implies second, second implies third, third implies fourth, and fourth implies 1. So both the four statements are equivalent, right? Now, if all the four statements are equivalent, then it means there is no difference between these four properties. If there is no difference between these four properties, it means continuous is a bounded and bounded is a continuous. So in the functional analysis, in the operator theory, we get all the continuous operator are bounded and all the bounded operator are continuous. So this is very important result. In the previous classes, we learned only continuous function are bounded, but bounded is not a continuous. But here both the statement are equivalent. Now we will start our result from definition. So I will take first is given, first implies second, right? So first means the function is, the operator is continuous at origin. To continuous, this is a continuous operator, T is a continuous operator, and second is continuous at origin. Now My purpose is to prove that second statement means T is continuous at origin. If T is continuous at origin, then it means I will take some sequence xn be a sequence in n such that this xn approaches to 0, right? So my purpose is to prove that Txn approaches to 0. Now by definition of continuity, since T is continuous, then by definition T of xn approaches to T of 0, clear, as n approaches to infinity. Since T is a linear operator, so what is this? It is a 0 of n dash. It implies Txn approaches to 0 as n approaches to infinity. So it proves our first result, T is continuous at origin. T is continuous at origin. Yeah, we can say that it is continuous at the origin or 0. Now second part. In the second part, the given is T is continuous at origin. Now second implies first, right? Now given part is T is continuous at origin, and our purpose is to prove that T is continuous. To prove T is continuous, let I take xn be a sequence in n such that xn approaches to x as n approaches to infinity, right? Then it means xn minus x approaches to 0 as n approaches to infinity, clear? So this is a sum sequence of yn, suppose. So this is some sequence yn which approaches to 0 as n approaches to infinity. By a given statement, T is continuous at origin, T of yn approaches to 0 as n approaches to infinity, right? It implies, what is T of yn? This is a T xn minus x approaches to 0 as n approaches to infinity, right? So what is T? T is a linear transformation. So by using the property of linear transformation, this approaches to 0 as n approaches to infinity. So T of xn minus T of x, it approaches to 0 as n approaches to infinity. Now it implies if Txn minus Tx, it approaches to 0, so it implies T of xn, it implies T of xn approaches to Tx as n approaches to infinity, right? So what we get? We get T is continuous function. T is continuous operator or function. So it means first is implies second and second implies first, and first and second are equivalent to each other. Now we start from second. Now second is given. My purpose is prove that third. So what is second property? It is continuous at origin. What is third property? It is a bounded. So that is given, and our purpose is to prove that T is bounded. That is my purpose. That is my purpose, to prove that T is bounded. Clear? Now we will prove this part with the help of contradiction. We know the definition of bounded set, bounded operator. Now, if second is, suppose this T is not bounded. Suppose this T is not bounded, right? This T is not bounded. Now that is for rough work. Just to see the definition. Norm of Tx less than equal to k into norm of x, right? It means if it is bounded, then it satisfies this property. Means every member of n satisfies this condition. Clear? It means there are number of members that does not satisfy these conditions. So we can find that number in term of sequence. So for each positive integer n, we can find a sequence, xn in n such that norm of Txn less than n into norm of xn, right? This condition. So we can find a one member where n is 1, second member where n is 2, and third member where n is 3, and so on. So it means we can find a sequence. So that is written as in equation number 1. It implies, what is this? Now this taken as alpha, this entire term is taken as scalar term. So in your mind, take it as alpha. If it is take it as alpha, so it will be 1 by alpha. Since 1 by alpha is again scalar, so in the norm it is shifted inside, right? Because it is positive number, so 1 by alpha, and this alpha is a absolute value of alpha because it is a positive number. So this can be written as norm T of xn over n into norm of xn, and this is greater than 1. Clear? So this is understand this step. So I will write in 2 steps. First is as multiplication, second then it will be shifted in this form. Clear? So to avoid confusion, so first when we divide, because it is a positive number, Txn, which is over n norm of xn greater than 1, right? These values. Now this term is alpha. So remember, this term is alpha. So this can be written as norm T. This will be inside norm. Then taking the definition of operator, this will be xn over n into norm of xn, this term is greater than 1 for every n. Clear this step? So simple calculation, so that will be converted into this form, right? So I can take 1 by n outside the inside. So that is a simple property of linear transformation. T of alpha x is equal to alpha of tx. Now this is again a sequence. So I put this xn over n into norm of xn, which is equal to yn. So this is a simple, this sequence, it implies norm of t of yn, which is greater than 1. So this is equation number 2. Write it as equation number 2. Now from sequence yn, just see that its norm is 1 by n. How? So norm of yn, which is equal to 1 by n into norm of xn over norm of xn, which is equal to 1 by n, and which is approaches to 0 as n approaches to infinity, right? So it means what we get? We get norm of yn minus 0 approaches to 0 as n approaches to infinity, right? What we understand from this? We understand this yn sequence approaches to 0 as n approaches to infinity. That we understand from this. But from equation number 2, t of yn is greater than 1. It means t of yn does not approaches to 0. Yn approaches to 0, but t of yn does not approaches to 0 because its norm is greater than 1. So that does not approaches to 0. If that does not approaches to 0, then t is not continuous at origin. T is not continuous at origin. Hence, our supposition is wrong, which is contradiction, because given part is t is continuous at origin. Hence, our supposition is wrong. If our supposition is wrong, then it implies t is a bounded operator. Then it implies it is a bounded operator. Clear? So it is a bounded. So 2 implies 3. Now 3 implies second part. So this is the second part. Third implies 2. What is third? T is bounded, and our purpose is it is continuous at origin. Now third is given, and our purpose is to prove t is continuous at origin. Now since we know that t is bounded, then it means there exists some positive real number such that norm of tx less than equal to k into norm of x. Suppose this is equation number 4, right? Now let xn be a sequence in n such that xn approaches to 0 as n approaches to infinity. So it implies xn approaches to 0 as n approaches to infinity. Now, by using this condition number 4, norm of Txn is less than equal to k time norm of xn, right? Since xn approaches to 0, so this approaches to 0 as n approaches to infinity. It implies norm of Txn approaches to 0 as n approaches to infinity. It implies Txn approaches to 0 as n approaches to infinity. It implies T is continuous at origin. T is continuous at origin. So third implies second. So second implies third and third implies second. So we reach at this step. First, if and only if; second, if and only if; third. Now, our next step is third implies fourth. This is third, it implies fourth. So what is third part? So third part is T is bounded. Third part is T is bounded. And what is the fourth part? Fourth part, in the fourth part, the given part is S, which is a bounded norm of x less than equal to 1. This is a closed unit sphere in N, and my purpose is the T of S is bounded. T of S is a bounded set. So this is a bounded set. Clear? So that is a fourth part. So this is a fourth part, and third part is it is a bounded set. It is a bounded operator, and purpose is to prove that the fourth part, so that is given. Now from this, given is third part, which is a T is bounded, then by definition of bounded, there exists a positive number. So since T is bounded, then by definition of bounded, there exists a positive real number k such that norm of Tx less than equal to k into norm of x. Suppose this is equation number 1 for this part. Now that is S, where it is a member of N where norm is less than equal to 1, and my purpose is T of S is a bounded set. Now for every x belongs to S, it implies norm of x which is equal to less than equal to 1. So it implies norm of x less than equal to 1. So it implies. My purpose is to prove this set is bounded. What is T of S? T of S is a T of X such that X belongs to S, right? So what is this set? This set is consisting vector Tx such that norm of X less than equal to 1, right? That's all. Clear? So this is a definition of Ts. So from definition and from equation number 1, we will get the result. Now equation number 1 is true for every x belongs to n, right? Equation number 1 is true for every x belongs to n. Now for this, now Tx, if T of x belongs to Ts, let this y belongs to T of S, it implies y is of this kind Tx, and where norm of x less than equal to 1, right? So what is norm of y? Norm of y, which is equal to norm of Tx by equation number 1, this is k into norm of x, and by this condition, which is less than k, and this is for every y belongs to T of S. It implies this T of S is bounded set. This T of S is bounded set, right? So this prove our result number 4. So third implies fourth. Now converse part. From the converse part, the given is T of S is a bounded set. Now converse part, fourth implies 3. So what is given part? Given part is T of S. T of S is a bounded set. Bounded set. It means norm of Tx less than equal to k. There exists some positive number k for every x belongs to S, right? Yeah. So simple. It's there exists a positive number. We just use the definition of this. So we get this condition for every x belongs to S. And what is S? S means all those members whose norm is less than equal to 1, right? My purpose is to prove that T is bounded. So our simply claim T is bounded mean norm of Tx less than equal to k into norm of x. That is my purpose for every x belongs to n, right? Now I will use this result. So remember this result. Okay? I will use this result. If x is 0, then this result is trivial, because T of x is T of 0 is 0, this 0, and it satisfies the condition of equality. So equality condition is satisfied. Now, if x is non-zero, so I am taking this non-zero. If x is non-zero, so put some y which is equal to x by norm of x. Why I take this? I take y because my purpose is to prove its norm is 1. If its norm is 1, then it will be belongs to S. If it will belongs to S, then it will satisfy this condition, right? So that's why I am taking this value, because my purpose is the norm of y should be equal to 1. If its norm should be equal to 1, then it belongs to S. If it belongs to S, then it satisfies this condition. Then it satisfies this condition. Now from this, norm of y equal to 1. So it implies y belongs to S. If y belongs to S, then this condition is satisfied. It means norm t of y, which is less than equal to k, right? It implies norm t, substitute the value of x by norm of x. This is less than equal to k, right? It implies this values. Now again 1 by norm of x is taken as alpha. So since t is a operator, t is a positive operator, t is a linear transformation of, then alpha into tx is equal to t alpha x. So what we get? We get 1 by norm of x into norm of tx less than equal to k. It implies norm of tx less than equal to k into norm of x, right? So it implies norm of tx, which is less than equal to k into norm of x for every x belongs to n. So it implies t is a bounded operator. So t is a bounded. It means all the 4 statements are equivalent. What you mean by this? It means number 1, if and only if. Number 2, if and only if. Number 3, if and only if. Number 4. So these 4 statements are equivalent. So we can choose any statement, one of them. Now if these statements are equivalent, then it means there is no difference between continuity, bounded, and continuity at origin. And number 4, if S is unit pair less than equal to 1, then T of S is bounded set. So there is no difference between all these statements, right? It means if it is continuous at origin in the functional analysis, if linear transformation is continuous at origin, so it will be continuous to any space, to entire space. If it is a bounded, then again it will be continuous. If it satisfies this condition, then all these 3 statements are also satisfied. The same in the case of other statement, right? So this is very important result for application as well as for examination. All the 4 statements are equivalent. So sometime theorem is asked in this way: prove that continuity and bounded are the same in this operator theory. Continuity means bounded, bounded means continuous. So that is our result.